Thank you very much. Thank you very much for inviting me here. As I said, so this is basically my hometown, where I grew up in Syria, so it's always nice to come back. Seems like the first two talks in the morning have raised the bar very high, but I guess at least there's chocolate after this talk, so so the other two talks didn't have that. Now, my talk, I guess, is the complete opposite of Mario's talk. So Mario's talk was much more like directed towards the future, right? And then sort of the visions of what he can do. My talk is more a bit sort of looking back at what we did the last 10 years. Maybe also see that I'm at the end of my year C grant. So anyway, so what I present here is really like a joint work with a number of people. So on the one hand, like there's Giuseppe Luisi and his research group at Chalmers. Some of his former PhD students. Then, well, Yuri Polyansky was involved in this line of research as well at some point. And then it's basically our group in Madrid. There's Alejandro Lanchos now at MIT, who was at my PhD. Chao was a postdoc, and Gonzalo was a colleague of mine at the University of Philadelphia. Okay. And I felt like it's a good starting point to ask the question whether wireless communications is still relevant. Maybe also a bit sad that we have to defend all the time that what we do is still relevant. But I think it's a fair question because so wireless communication has been a very hot topic that is until not so long ago. But now recently it has lost a bit of prominence. The question is it really worth still working on that? And obviously I wouldn't give this talk if I wouldn't answer this question with yes. That would be even more sad, right? And I think, well, there's still a lot of interesting things we would like to do, and we have visions for the future. I guess some of those are sort of surrounded the concepts of the Internet of Things. I mean, Marius was also talking about that a little bit, right? So yeah, the idea of Internet of Things is that we connect not just people via the Internet, but also different things. And then there are different sort of sub-concepts there. So one would be Industry 4.1. The other one would be like smart transportation, where vehicles communicate with each other to increase traffic safety. There's also things like e-health, smart cities, etc. And I think that the backbone of all those applications is still wireless communication. So if you want to somehow connect all those devices, you need to have a connection, and this connection has to satisfy certain constraints. Okay. And there's still some challenges. So there's some, again, also Marius already mentioned some of those challenges we have. Maybe I should have synchronized with him when I prepared the talk. For example, like what we want from next generation wireless systems, like on the one hand, we want to have high data rates, but on the other hand, we want to have low end-to-end latencies. And jitter is now the new thing that people talk about for next generation, right? They need to have a high reliability. We may have to connect a massive number of devices, which is some of the things that are very difficult. I guess we understand very well how point-to-point works, but networks is a whole completely different field, especially if there are a lot of devices. And then they also talk about autonomous networks that sort of can like configure themselves using automation and intelligence. So there are a lot of interesting things that we expect next generation wireless networks to do. Yeah. Now, so if you talk about like how to design a communication system, I guess the classical approach, and also Marius again talked about this a little bit, but the classical approach would be that we split up the transmitter and the decoder into different subblocks, and then we optimize them separately, and then we put everything together. Right. So I guess sort of the most classical way would be is we have a source encoder that compresses the source, then we have the channel encoder that adds redundancy to correct errors, and then you have the modulator that produces the waveform that is transmitted over the channel. Right. And then at the decoder, you would have sort of the corresponding blocks. And I think traditionally what we usually did is we assumed some model for this channel here, for example, that could be a Gaussian channel or something more complicated. And then we had a lot of theory that helped us sort of figuring out how to design these blocks in the optimal way or in a good way. And I think I would say this is sort of the classical approach to a communication system. And again, the modern approach would be to use machine learning for wireless communications to design those blocks. And I believe you guys know much more about this than I do. So from what I understood, there are basically two levels of doing that. So one level would be that you just use machine learning to design some individual receiver processing tasks. You could do decoding or equalization or channel estimation, and you could use machine learning to do these tasks. And I would say this is something that is very natural, especially for information theory, it's coding theory. Because in a way, like a decoder of modern error correcting codes, like LDPC codes, turbo codes, they already use message passing algorithms in their decoder. So it's not a very big step, I guess, than applying the same knowledge to other tasks, let's say equalization, for example. And then another level would be that you use machine learning to design the entire communication system. So that you would basically want to learn the full transmitter and receiver implementation for a given channel. I think so what I understood, I'm not really an expert on that, but what I understood is the idea is that you somehow model all those blocks in the transmitter as neural networks, and then you can treat the whole model as an autoencoder, and you can sort of try to learn what is the optimal structure. Okay. Again, I hope that you understand much better what that means than I do, because it's not really my specialty. But there are people working on that, right? You can find literature on this topic. For example, there's a paper by Jacopoidis that introduces deep learning for the physical layer, where he explains this a little bit. There are other research groups working on that too. Like Fernanda knows about these things a little bit as well, I guess. There's a group in Stuttgart, right, Stefan van Brink, who does work on that. So there are people working on it. And I think like with any sort of new approach, there are always some chances and some challenges. And I think the chances are of that, especially if you design the entire communication system jointly, is that you can really do a joint optimization of all the building blocks of a communication system. If you think about it, like splitting up your transmitter in these 3 sub-blocks is not the best thing you can do. It's good enough if you care about capacity, but already if you look at finite block length, like error exponents, for example, this is suboptimal. So by doing this, you could actually learn the entire system. Plus, like in the classical approach, we always need like a good model for the channel, and it should be something that is tractable so that we can do math with it and we can understand it. Whereas if you would learn just everything, you might actually be happy with a channel model that is not as nice to write down. I mean, I even also saw like applications, not in wireless communications, but in fiber optical communications, where the channel model is described by a differential equation, and then that you cannot write out in closed form, but you can actually find a graphical model that somehow describes it. And you could even like optimize then a communication system for this scenario if you just learn everything in your like numerically. Now, on the other hand, there's some challenges. I guess one is computational complexity, especially if you want to look at long code words. I'm not sure whether this is something that still works very well if you have like a lot of parameters of which you want to optimize. But I mean, for me as a theoretician, I guess more important is the second. And this is the belief that the performance of your learned system actually will depend on a number of design choices you do when you try to learn the system. Right? You have to figure out what kind of loss function you use to optimize it. You have to decide what kind of type of neural network you use, etc. And these are all design choices that you cannot really, I guess, verify whether these are good or bad. Like you choose something and it might work well, but you don't know, could you do better if you model the whole thing in a different way. Right? But again, I'm an information theorist, so I care about these things. Maybe you're just happy with convergence. But I think this is still something where information theory could actually provide something to the design of communication systems, even if you say we're done with the classical approach of doing everything based on theory. Because information theory can actually provide us with theoretical benchmarks that tell us what would be the optimal performance of a communication system. And then you can still design your communication system trying to learn it, but you can compare the performance of this with your theoretical bounds, and then you know whether your design was a good one or bad. Okay. I think in the old disinformation theory thought, like by doing this theory, we give good insights on how to build the communication system. I'm not convinced that this is really the case. At least in coding theory, I think the way we design LDPC code has nothing to do with what you learn from analyzing capacity. So I'm not sure that this is true, but I still think the benchmarks themselves is actually something that can be valuable, even if you're sort of, let's say, your interests are less theoretical. Okay, so judging from the title of your ITN, I wasn't sure how much you know about information theory or not. I went later to the webpage and I believe that you know enough, so maybe you wouldn't need this slide, but just to go quickly over like the way we would model a communication system in information theory. The idea is basically that your source is a sequence of bits, so basically a sequence of IID Bernoulli 1/2 random variables. Then the encoder is nothing else than a mapping from those bits to some sequence of symbols you want to transmit over the channel. The number of symbols we refer to the block length. And then we transmit those symbols one by one over the channel. And at the decoder, we wait until we receive all those end symbols, and then we decode them, right? So we try to get, based on this observation, what the bits were that we transmit. And I guess that's where the name block length comes from, because you do like a blockwise transmission, right? You take a block of bits, map it to a block of symbols, and then you do blockwise decoding. Which I think is not a bad description of nowadays communication systems, because also there we transmit information usually in packet, which is also like a blockwise kind of transmission. I think there are basically two important figures of merits we care about. So one is the rate, that would be the number of information bits divided by the block length. And then the other one would be the probability of error. So in this case, I look at the block probability of error, simply probability of error. And then the goal is to find the optimal trade-off between rate and probability of error for a given block. So this is what we're after theoretically. And I mean, this already has been studied by Shannon. And he looked at a very specific trade-off between these parameters. So he looked at the case like, what is the largest rate that should the probability of error tends to 0 if the block length tends to infinity? And he named this rate channel capacity. He actually showed that for a memoryless channel, you can write the capacity. So you have a formula at channel capacity. Just given the mutual information between channel input and output, maximize the overall input distribution. Now, in finite block length information theory, we would like to understand a bit better this trade-off between rate and probability error for given block lengths. So we have to look at something that is a bit more refined. This is the so-called maximum coding rate, which is nothing else than the largest rate for which we can find the channel code of the block length n, such that the probability of error is not larger. If you want, this is sort of the best rate you can achieve if you have a block length n and the probability of errors. And obviously know from Shannon that this maximum coding rate will converge to capacity as the block length tends to infinity. But in finite block length information theory, we would like to understand better how this rate behaves as a function of the block length. Okay. And now, why is this relevant, or why do we care about this? Well, it turns out that the latency of a communication system is proportional to the block length of the code we use. So let me go back maybe, well, here in this figure is not so bad. So we said we do blockwise transmission, so you have to wait until you receive all the n-channel output. And which means that this waiting, of course, this determines how much latency we have. So more precisely, the latency depends on the one hand on how many symbols you have to wait for, and on how fast you can transmit those symbols, right? How many symbols you can transmit per second. Now, the number of symbols you can transmit per second is determined by the bandwidth. And bandwidth is something that is valuable, so this is usually fixed, which means that the latency you have is pretty much proportional to the block. Now, channel capacity implicitly assumes that the block length tends to infinity. So if you have a latency constrained application, actually channel capacity itself might not be a very good benchmark for your system. Right? And this is sort of a finite block length information here concept. Okay, something like that. Okay. Now, in finite block information theory, basically have 4 types of different results in our toolbox. On the one hand, we have bounds on the maximum coding rate that hold for a given block length n. So these are non-asymptotic in the block length. And then we have like 3 different asymptotic expansions of those bounds that are less accurate, but they may be a bit more intuitive. The first one would be error exponents. So for error exponents, we fix the rate, and then we study how fast the probability of error tends to 0 with the block length. Turns out this decay is exponential. Then you can determine how large this exponential is, and this is the so-called error exponent. So this is, again, this is very old. I mean, that already Shannon worked on this himself, Gallagher and so on. That's very old school. Then we have a normal approximation. So here you fix the probability of error and you study how fast your rate converges to capacity. So in other words, you pretty much approximate your rate as the capacity minus some backoff term. And the backoff term is proportional to 1 over the square root of the block. Okay. And this has received a lot of attention from some work by Polyansky, Poole, and Verdun in 2010. But it actually goes back to Strassen. I think that's also in the 60s. So and then the last one, which I think is a bit newer, especially applied to wireless communications, is the Saddlepoint approximation. So Saddlepoint approximation has been around also since the 50s, but I think it has been more applied in the 50s. I will present this. I think this is a very nice way of evaluating this stuff. Okay, so let me start a little bit with the bounds we have. So there's actually tons of bounds in the paper by Polyansky, Poole, and Verdun. The bound I'm going to just show you here to give you an idea of what these kind of bounds look like. This is the so-called RCUS bound. So RCU stands for random coding union bound. And then the S is like an additional parameter that we have in this bound. This bound is actually by Alfonso Martinez and Albert Gianni-Fabregas. And it says the following. So it says, like, for any distribution of my n channel inputs and any parameter S, we can find the code of rate R such that the probability of error is upper bounded by this probability. And then here, okay, so U is a uniform random variable. And what we have here, this is the so-called generalized information density. This is just, so here we have the distribution of the channel, this is like the channel log. And then down here, we channel log to the power of some parameter S. And then here it's the same thing, but averaged over all the inputs according to this distribution that we chose. Okay. I guess the important message here is basically, so you have a bound, and most of the time you actually should be able to evaluate this numerically, for example, using Monte Carlo simulations. Okay. We want to have upper bounds that mainly, I guess the main bound we use is the so-called meta-converse bound. That's also in the paper by Polyansky, Poole, and Verdun, which says that for every parameter psi, we can upper bound the maximum coding rate by this expression here. And again, so the difficult part in here is this tail probability of the so-called mismatch information density. So here we have the logarithm. This is again the channel log, and then we divide here by some auxiliary distribution on the output output. So this can be any arbitrary distribution, and for any distribution we get an upper bound. But if you have to pick a good one, such to get in order to get a good bound, okay. And again, this is something that probably in closed form you cannot evaluate this, but you can evaluate it there. So I mentioned that already before now. So in here we basically have this distribution P of y given x, which is nothing else than the channel that we have. So there would be enter the channel model. So if you want to apply those bounds for wireless communications, then you would have to choose for this conditional distribution a model that models sort of your communication medium well. Okay.
This not relies on the fact that the distribution of X input is very limited in the distribution. Or is it?
No. So the bounds themselves, they make no assumption on the inputs. Yeah. So these are, I mean, they sometimes call them one-shot bounds. So there are no a priori assumptions on the distribution of the input. I mean, later on, if you want to evaluate those, you will make some assumptions, for example, liable input. But that depends on the channel. Fine. So yeah. So I said, so if you want to specialize those bounds to our specific problem, then we have to choose the right model here. And so basically, what we're after a model that captures the most important trade-offs we have entire wireless communication system. So that could be coherence, time, bandwidth, channel estimation overhead, perhaps trade-off between diversity multiplexing, etc. So we know all models are wrong, but some of them are useful, right? And I guess a useful model is the one that at least is able to capture some of the trade-offs you want to understand. Now, a common channel model that people in the literature use is the Rayleigh block fading channel. Again, this is not necessarily the most accurate model, but it's a very common one, so it's well recognized, and it at least covers the trade-offs we're interested in. So the Rayleigh block fading channel, for those of you who haven't seen it before, it's a model that basically has additive noise and multiplicative noise. And we assume that these noises are zero mean Gaussian. So this is where the name Rayleigh is coming from. Now there would be like a multi-antenna version of this model. In this talk, I will just focus on the single antenna case because things become a bit easier. In principle, generalizing. And now block fading refers to the fact that this fading here is a blockwise IID process. So the fading coefficient stays constant for T symbols, and then it changes to something that is independent of what was before. Okay. And well, by changing this parameter T, you can somehow model slow fading, fast fading. And then we have the parameter L, so we call it number of time frequency branches. It's basically just the number of times you can fit in T symbols in your code of block length N. Okay. So basically your code word consists of L blocks of length T, somehow the end. So we usually like to group inputs together in T blocks because then we get a channel that is which channel is meant. Now, in our work, we assume that we don't have a priori channel state information. So neither transmitter nor receiver know what the realization of this fading coefficient is. But they know what the distribution is. So the distribution is Gaussian. And I think, well, we believe that makes a lot of sense because having access to the realization of this fading is actually, for this you would need to pay for, right? You don't get this for free. For example, if you want to get the knowledge of the fading at the receiver, you could transmit pilot symbols, right? So predefined symbols at predefined locations. Then you could estimate your fading coefficient. But if you do that, you waste rate, right? Because in the time where you transmit pilot, you could actually also transmit information. And if you look at the sort of case where you don't have this knowledge at the receiver, then you can still use this strategy as a possible coding scheme. But then you have to account for the loss in rate for doing this. So by assuming that you don't have this knowledge a priori, you can actually study how much you pay for not knowing the fading. So you basically get sort of the channel estimation cost reflected in what you do. Good. Let me just briefly look. So that would be the maximum coding rate specialized to the wireless communications part. So this is pretty much what I defined before. I guess the speciality here is that now I group my channel inputs into a block of T symbols. Right, so instead of having N symbols, I say, well, I have L vectors, each of them dimension T, that I transmit over my channel. And again, like this, I end up with a channel that is again memory. So these are the kind of channels that we like. And then, well, that's is common. We have a power constraint because you cannot transmit with infinite power, right? With no, well, if you could achieve an infinite rate, so that would be great. But of course, you cannot design your system like that. There's always a constraint on how much power you have to use. In our case, we assume a per block power constraint. So in each coherence block, we want to limit the power by something. Which I think, like for a practical system, it's not such a bad assumption. It also makes the analysis easier for us. So good. That's not too bad. And then we look at here probability of error. And again, we define the maximum coding rate as before. So this is the largest rate for which you can find an encoder and decoder satisfying the power and the error probability. Alternatively, we could also define the minimum error probability, which would be the smallest probability of error for which you can find an encoder and decoder satisfying the power constraint and having a given rate R. And the two are equivalent. So if you have an expression for this one, you could get this one and vice versa. But sometimes it's easier to sort of present our results in terms of maximum coding rate, and sometimes it's easier to present it in terms of minimum probability. Good. But now what we want to do is we want to take those bounds that I showed you, and we want to evaluate them numerically. And if you want to do that, so what you would have to do, so for the RCS bound, you would have to compute this probability. And for the meta-converse bound, you would have to compute this probability here. And well, again, as I said before, so doing this in closed form is most of the time not possible. But you can do it very often numerically. So it turns out that because we have like this block IID sort of nature of our channel model, we can write these information densities as sum of some functions that are known functions of two IID gamma distributed random variables. Okay. So we have to write it down, and there's some underlying assumptions that I will skip over a little bit. But in principle, so you can write those as sums of IID random variables. And given that these are gamma distributed, so it's either easy to draw from them like in numerical programs, so then you draw those at random, you could evaluate the functions, and then you can evaluate these probabilities using Monte Carlo simulation. Okay. So this is something that is not very difficult to do with Monte Carlo simulation, because you have closed form expressions of this. Good. Now, just to see how good the bounds are, so what we plot here, for example, is the maximum coding rate as a function of the coherence interval if you fix the block length. So we fix the product of L times T to be 168, which I believe is a reasonably short code. And then the product here is held fixed. So if T increases, then L has to decrease. And then what we see here, so this is for 60B, which I think is not too bad either. So we see here, that will be the upper bound, meta-converse bound, that will be the RCOS bound. And we know the maximum coding rate is somewhere in this shaded area. Okay? Which I think is a reasonably tight bound to sort of use as a benchmark. So you pretty much know you're somewhere around. We have another plot where you show the maximum coding rate as a function of the probability variable. And again, so again, the total block length is 168. And again, you see that the sort of you have the upper bound, lower bound, and they describe pretty well where the maximum coding rate is. So I think for these sort of problems where you have like a Rayleigh fading, you get a very good idea of what the best is you could do. So they're very accurate. And I mentioned that before, you have to compute them numerically, which is fine. But I guess the problem is that that can be very expensive because the computational cost grows exponentially in L. Okay? Because if you have here like the block length of L singles, right? So you have the sum of L terms. So you have to compute a lot of integrals to solve this thing. That is actually exponential in L, which means if L is large, then this will become very expensive at one point, right? So to simulate one point, maybe you have to like 2 weeks or so, which is not something you necessarily want to do. You don't have to. However, the good news is that I mentioned before that you can write those information densities that are in here as sums of IID random variables. And we know in statistics, sums of IID random variables is something we like because we understand very well how their tail probabilities behave as n tends to infinity. Right? So usually as n tends to infinity, they start to concentrate around the mean, and then we have a lot of knowledge about it. So you can use this knowledge, and then you can form asymptotic expansions of these bounds. And that will definitely be easier to evaluate and hopefully more intuitive. Of course, on the downside, you might have to sacrifice a bit of accuracy, but there is no free lunch. They were just like you sort of briefly repeat sort of the tools we have in our toolbox if we care about sums of IID random variables, also because I think it's interesting in general. So suppose we have here like a sequence of IID zero mean random variables. Now we know if we look at the average of these random variables, at one point this will converge to the mean, the zero mean, but this will converge to zero. And I guess the easiest result that we have on this result is that we know that this converges to the mean in probability. Right? This is the so-called weak law of large number. So the probability that this mean is larger than some arbitrary epsilon will tend to. Another type of result is large deviations. In large deviations, we look at how fast this probability tends to zero. And it turns out it tends to zero exponentially fast. So if you look at the limit of 1 over n times the logarithm of this probability, then you can characterize this too. So this sort of characterize the exponent of how fast it is. And now in here, because we have to solve the sub-optimization problem here, where this thing here, this is so-called cumulant generating function. So it's the logarithm of the moment generating function. Now another type of result looks at the different scaling of this sum, right? If you scale by 1 over square root of n instead of 1 over n, then you know that this will converge to a Gaussian. And this is what the central limit theorem tells you, right? Now, the central limit theorem basically tells you convergence in distribution. So here I have a slightly stronger result, which is the variation theorem, which basically compares the CDF of my scaled sum of random variables with the CDF of a standard Gaussian, and it shows that this decays like 1 over square. Okay. And something related to that would be Edgeworth expansion that sort of goes in the same direction. I think that this is pretty much the toolbox that we have. And now if you apply this toolbox to the non-asymptotic bounds, we can obtain asymptotic expansions of the maximum coding rate, for example, that can be very useful. So just as a side remark, if you apply the law of large numbers to those bounds, we directly recover a channel capacity. If you do large deviations, we would recover what we call the error exponent. So we can look at the minimum probability of error, and then asymptotically, the exponential decay of this one will be equal to this expression here. So here, this term here, this is nothing else than the cumulant generating function of our information density. So now you treat the information density as a random variable, you compute this cumulant, then in here you would have the first derivative of the cumulant. And this tau that we have here, this is the parameter which solves this equation, okay? So if you want to figure out how fast your minimum probability of error decays for a given rate, then you would first have to solve this equation to get the tau. And then once you have the tau, you can plug it in here, you get an expression, okay? And with this, you get the closed form approximation of your minimum error probabilities. You get that this minimum probability of error is e to the minus L times this thing, okay? Now I say here, well, you just compute the cumulant. Now, very often in closed form, again, this is something you cannot do, but it's definitely something you can do numerically. Okay. And computing this numerically does at least not depend on the block length. So the complexity is always the same, no matter how long your block length is, which is nice. And then the same thing for the first derivative. So that would be another numerical integration that you would have to do. Right, now if you would do central limit theorem, then your bounds would give the so-called normal approximation. The normal approximation would look like something like this. So you have here like a capacity minus some term that decays like 1 over square root of L times here we have the inverse of the tail probability of the standard Gaussian, the inverse of the Q function, right? And then here, so this channel capacity is nothing else than the mean of your information density. So if you have the information density, this is for parameter s equal to 1, then you can compute this by computing the mean. And what you have in here, that would be, well, that we call channel dispersion. This you get by computing the variance. And again, if your channel model is complicated, like the radial block fading channel, then you might not be able to do this in closed form, but you can actually do it numerically. Okay. And again, this computation does not depend on the block length, which is nice because we look at block length of, I don't know, maybe 168. And now if you look at different coherence blocks, so then L is, I guess, large enough that having something that grows exponentially in L is not so much. Okay. So with this, we get a closed form approximation of our maximum coding rate. And now let's see how much we lose in terms of accuracy if you do that, because I think it's obvious that they are nicer than the non-asymptotic bounds themselves. So again, this is the same block we had before, like maximum coding rate versus coherence interval, and we fix the block length. We have here the bounds. Now, if you show here this approximation, so the error exponent approximation is somewhere around here. The normal approximation is this line. Okay? So they're not as good as the bounds, but they're also not horribly bad as benchmarks. Perhaps more interesting is this plot where we show the maximum coding rate as a function of the probability of error. Because there we see that these two approximations that we now have, they have a crossing point. So the normal approximation is good if my probability of error is not too small. And the error exponent approximation is good if my error probability is small. Okay? Which I guess is a little bit worrisome if you want to use them as benchmarks, because now it means that you have to be sure that you use the benchmark in the right regime, right? And for that, you need to have a bit of knowledge of where those approximations come from. So what we were really after were benchmarks that work equally good for all the parameters. And this is where the Saddlepoint approximation comes into play, because the Saddlepoint approximation generalizes both the normal approximation and the error exponent. So they're accurate in both of those regimes, small probability of error and large probability of error. Again, sort of going back to our channel expression. So again, we have a sequence of IID zero mean random variables. Now, what the Saddlepoint approximation tells you is that if those random variables are so-called non-lattice random variables, and if their moment generating function is bounded on an open interval, then you can approximate tail probability of this average in this form here. Okay, so now what do we have in here? So this is again our cumulant or cumulant generating function. And here this is a second derivative. Here that will be the Gaussian Q function. And then here with this parameter tau, we have to choose such that the first derivative of the cumulant is equal to the C. So C is the parameter. Okay. Just let me first quickly explain what a non-lattice random variable is, and then I sort of explain why this is useful. So to define a non-lattice random variable, we actually have to define a lattice random variable first. It's a very mathematical sort of definition. A random variable is lattice if it's supported on a lattice, simply enough. And it's non-lattice if it is not lattice. Okay, this is the way you define it. And you can show that it's non-lattice if and only if the characteristic function is bounded away from 1 for every sector that is not 0. So you know at 0, this is 1 anyway. But if your random variable is not lattice, then it somehow decays. And if it would be lattice, then it would be 1 in periodic intervals, right? So this is sort of the big. Anyway, now this one, I guess we all agree, is not as nice as, say, the central limit theorem, for example, like if you look at it. But still, from a numerical perspective, what you need to compute to get this here is just like the cumulant generating function, the first derivative, and the second derivative. And if you have those evaluated numerically, you can obtain the rest in closed form. So basically, what you have to compute is much simpler than having to compute the non-asymptotic bound directly. This is, I think, what we like about. And you can sort of specialize this to the RCUS bound and the meta-converse bound. So then that would look like something like this. So we could upper bound the minimum probability of error by this expression. So here again, this would be the cumulant generating function of our information density, which looks not nice, but you can compute it numerically. And you would have your first derivative, and then you have here some terms here that are available in closed form. Okay, so that's simple enough. And again, tau is a parameter that you obtain by solving this equation here. So for every different rate that you would like to have here, you have to choose a different tau. Again, nothing you cannot do numerically. Now, for the meta-converse bound, it's the same thing. You get a somewhat slightly different lower bound. But again, what you need to compute is you need to compute the cumulant generating function plus the first 3 derivatives. And if you have that, you can get those bounds. Okay. Now, again, if you want to see how accurate they are, so this is the plot we had before with the bounds and the normal approximation, Eric's point approximation. And this is what you do when you get the saddle point approximation. Now, here I changed a little bit what I plot. So here the dots, this is what you get if you compute the non-asymptotic bounds at those points numerically. So these points are sort of expensive to obtain. And the solid lines, this is what you get if you take the saddle point approximation. And you see that you basically lose almost nothing. So there's almost no loss in accuracy. So they're very tight, especially because what you have to compute numerically is much simpler. Okay. Same thing with this plot here. So here we have these dots, which are the non-asymptotic bounds, and the solid lines, which are the saddle point approximations. And we see here when we can compute the saddle point approximation also for very small probabilities of error, something that we were not able to do with the non-asymptotic bound. You can even go here to 10 to the minus 10, which are reliabilities that might be relevant for next generation wireless systems. And where with the non-asymptotic bound, there's no way you're going to go down that low. So here we have another plot. I think this is the one that coding theorists like, right? So this is probability of error versus SNR. You fix the rate of your code, and you want to sort of see how fast this decays. Right? You want to sort of know where is this waterfall region. Only that finite block length, you don't really have a waterfall region, right? But you somehow know how this decays. So again, the non-asymptotic bounds would give you these points, and the saddle point approximation would give you these lines. So this is very good. And much better than if you would do, let's say, normal approximation or Eric's point approximation. And what we have here, so here, this is the performance of some, let's say, semi-practical coding schemes, where we use ordered statistical decoding with scale nearest neighbor decoding, and some, I guess, off-the-shelf LDPC code. You see, you're not doing so bad, but there's still, I mean, we're not talking about 0.1 dB that we use, right? So it is more than that. I guess it might be interesting to see, like, where's the performance of some communication system learned by machine learning in this plot. Like, how do you go? How good do you get there? Right. Now, I talked a lot about complexity, so let me just highlight this here again. So if you want to compute the saddle point approximation, basically what you have to compute is mutual information. So this is the mean of our information density, then the cumulative generating function, first derivative, second and third derivative. So there are basically 5 integrals that you have to compute. And this is independent of the block length. Whereas for the non-asymptotic bounds, you'll have to compute this mean, and you have to compute this tail probability. And this one becomes very difficult to compute if L is growing. Now, if you look at accuracy, so we have seen that the saddle point approximation is very accurate. So you lose almost nothing in terms of accuracy. So which is why we believe that it is a very easy to compute alternative to the non-asymptotic bound. So if you, I don't know, if you try to learn a communication system, maybe try to compare it to the saddle point approximation and see where it's at. So I can understand why you wouldn't want to do it with the non-asymptotic bound. But I guess with the saddle point approximation, it's worth a try. And if you compare it to other asymptotic expansions, so we have normal approximation, their exponents, which I think are a bit more intuitive than the saddle point approximation, but they're also only just good approximations in different regimes. The normal approximation is good if the error probabilities are not too small. Error exponents are good if the error probabilities are small. And if the saddle point approximation, you really get an accurate approximation over the entire range of system parameters, which I think is something that is nice if you use a benchmark, because you don't have to worry about whether your benchmark is really good in this regime. Also, one can actually show that by starting from the saddle point approximation, you can recover these 2 approximations. So this is really a generalization approach. Now, as I said, so this is pretty much 10 years of research. So we have tons of, so there are a lot of more things to mention, subtleties, details, etc. So I just scratched here on the surface. There's some publications you could read if you want to learn more about it. I mean, that one here is now already an old paper, I guess. I think like a tutorial paper on finite blocking information theory for wireless communications. And we have some work on MIMO regulating channels, some work on normal approximations. And I guess if you want to learn about the Saddlepoint approximation, you could have a look at our paper in transactions in wireless communications from 2020. So there we really produce all those powers. Yeah, and that basically brings me to the end of this talk. So I still believe that no matter how we want to optimize the communication system, I still believe that information theory could be useful, and if it's only to give you theoretical benchmarks and tells you how good those designs are. And yeah, well, we have here a number of different tools in our toolbox. So one would be the non-asymptotic bounds, and then we have these 3 different asymptotic expansions that somehow all have their own values and they work, I guess, in different ideas. So these 2, they're a bit more, let's say, intuitive to analyze mathematically, but they're not that accurate. And then we have the Saddlepoint approximation, which is more difficult to analyze mathematically, but it's very accurate. And I think in general, even if you're not so much into wireless communications, I think Saddlepoint approximation should be a tool that is interesting to anybody who wants to know about some of the independent random variables, which is, I guess, pretty much any problem that we work on, right, some way or the other. So if you have to sort of get a hand on the K probability of the sum of independent random variables, I think Saddlepoint approximation is definitely something you should try to get something really very close for. And that's as much as I want to say about this part. I don't know whether there are any questions.
Anyone, why are they called Saddlepoint approximation?
Yes, took me a long time to understand it. So there's, let's see, there are various ways of defining or obtaining the Saddlepoint approximation. I think the original way was via Laplace transform. So you look at the tail probability, and then you look at the Laplace transform of this. Right now, it's a sum of independent random variables in the Laplace transform. It's a product of it's a product of terms, and then you have some exponential term in there with the cumulative generating function. And then what you do is you do a second order Taylor series expansion of this exponent, and you do that around the saddle point of your function. And that's where the name Saddlepoint approximation is from.
On the shape of the
right. So it's sort of like it's where you approximate your Laplace transform. So I have in a slide that I wrote it down. If you're interested, I can show you later. But this is
the second question is concentration inequalities are tailored for information theory from this communication problems, or are they taken from the large literature of concentration inequality?
Oh, I mean, so everything like law of large number, etc. I mean, this is statistics 101, right? This is best known secrets. I mean, this is from mathematics, right? I mean, that goes way back. That's much older than. But I mean, I wrote that down because okay, I care about these kind of things. I guess nobody else in my group does, but let's see, for example, right? So here we have large number is nothing else than Markov's inequality. I don't know back to when this goes. I mean, this is to Kramer. I don't know when he lived, right? That's a long time ago as well. They use channel-bound exponential field. So I think this is really the toolbox we have from statistics that hasn't changed much in recent years. But it is, I mean, the probability theory did evolve a lot since Kolmogorov, so it's not such an old field. But it's this is much more channeled in communication.
So the challenge is to transfer those tools to the specific quantitative information that.
Right. So it's, I mean, even the Saddlepoint approximation, I wrote this down here somewhere. So the first one to really apply to statistics was Daniel in 1954. And he had nothing to do with information theory. So this is something that's been around and it's been used in finance as well. So there's nothing new if you want there. But of course, understanding that you can use those tools and you can apply to communication theory, at least with the Saddlepoint approximation, is something that I think Alfonso Martinez, Alberti, and Fabregas were some of the first who said, hey, why don't we use these, which are used in physics, for example, implied there.
And so how do you see the future of skill? That how do you see the future of skill develop? Like a work of finding those two back in the literature from 15 years ago, or developing something?
I mean, I think that, so in general, if we talk about information theory, the implications to wireless communications, right? So then I guess we're a bit of in a sorry state, in the sense that I believe that we still do things that are important, but it's not really sexy talk, so right? So people are not really care about that much, right? So, so I would probably not recommend a PhD student to start working on that again, because it's just like nobody cares, right? And I feel like also like at least this part of finite block information theory is now ready for other people to take over and use it as a tool and sort of see whether it's really as useful as we believe it is. I don't think that this is something that somebody who's young should start working on. It's not very gratifying. And of course, there are other problems, for example, like Mario's talks, where there are more, I guess, more open challenges where you really can work for a long time to just find. I would really see that one is at the verge of sort of going on to the next step. But I think sadly enough, there's not enough people in, let's say, more applied fields who dare to use these kind of tools, I think, in their work. And I think this is sort of one of the things we should do. We should bring it to those people, right? And I guess you guys at least have seen some of the titles of the talk where you want to design communication systems using machine learning, for example. I think that would be nice complement to those things.
Yeah, but I mean, what do you think when you really don't have those assumptions that you should make about synchronization from the channel? We have to still work on that, try to characterize as well.
Yeah, synchronization is a challenge, definitely. I guess for point to point, it's not so bad because you somehow can synchronize, right? It's an art technique. If you go to networks, of course, it's a whole different situation. And I think networks is still the big challenge. Anyway, so yeah, I think it's a very important problem, but I haven't seen anything that really.
I don't know if the space, for instance, that they have to, innovation as a channel, and this coherence and independent mind. And then you have a specific bound for the channel.
Yeah, I wouldn't be aware of much work in our literature, I think, because it's theoretically so difficult to. But I mean, actually, we do have some work on the multiple access channel where the transmitter were not synchronized, and then you have to assume certain waveform you assume, and you obtain a channel with memory, which is more complicated, etc. But there's definitely a lot still to do, and I'm not sure whether there are like the right spark, the right ideas to really make any progress there. It's a good question.
Since you mentioned the end-to-end learning, the output at the beginning, now to close the loop, if you apply this autoencoder idea of brute force, you're limited to very, very short block length. But that's in a regime where not even the Saddlepoint is very good. You don't have fine upper and lower bounds that are capable of covering the regime of block and 10, 20, 30, or is there something there?
Good question. So I think what you observe is the Saddlepoint approximations are actually pretty good in large range. But it's true that if your block length is very small, then I don't know whether maybe then you're better off really evaluating the non-asymptotic bounds, right? So then maybe that part might still be possible.
I think to give gap prices,
That might be.
there's not a good, framework that bridges the gap between very, very short codes, like on the order of n lower than 10, and kind of.
I mean, what you always can try, right? This is like sort of Taylor series sort of idea that if it's not accurate enough, you just add more terms to your expansion, then it should become more accurate. Right? So in principle, the Saddlepoint expansion that we do, let's see. So this is basically based on the so-called Edgeworth expansion. And you can add always more and more terms to get actually more refined or more accurate approximations. In principle, you could refine the Saddlepoint approximation by adding more terms, and then it should be more accurate for smaller block lengths. Of course, the negative part of that is, on the other side of the matter, is that it gets more cumbersome, the whole expressions that you have. But in principle, you can add more terms to make it more accurate. But then you would have to, I guess, somehow evaluate it for the specific problem and see whether it's really accurate in this regime that you're interested in, right? But I'm not aware of, let's say, any other tool that would be very good in this intermediate thing, right? Yes.
Curiosity, we have taken. Does it look nice or like, because Boyansky read a paper very nasty on the mind of case when you have all these matrices to calculate some really steep expression. You can use random matrix theory, still then it's hard to get it.
Yeah, we're looking at that. It's true. So basically what happens, right? So just that everybody's on the same page. So in the single antenna case, you basically have here these gamma distributed random variables, you apply a function to it, and it sum up. If you go to MIMO, then you have to look at singular values of some matrices. And yeah, this is the mess. Now, in principle, it can be done. Because you can evaluate the Saddlepoint approximation. It will take you more time to evaluate it, so it becomes more expensive to do it. So we're still sort of working on it to sort of see like how good this can be. But so in principle, it can be done, but it's getting rather cumbersome exactly because of this. Because if you look at, so usually the input distribution we use is USTM, and then the corresponding output distribution of this. Sort of you need to compute some singular values of some matrices, etc., which you can do, and you can do it numerically, but it's not very nice. Yeah, so this is
Either the one singular than the one for Janssen.
So, but what exactly is the one you're referring?
I mean, remember the often.
Right. So okay. So what Polyansky and Austin do is actually the case where you have channel state information at receiver.
Not in the same framework.
Exactly. So this is somewhat a different regime. Right. So there they really try to get a normal approximation, and we're sort of doing that as well. So they really try to do something in that, and we're sort of in the process of doing that too. And you can do it. And the expression you get. It's a little bit nicer, I think, than what Polyansky gets there, just because it's USTM input distribution as well. It has disadvantages, but also it has some advantages, at least for the power constraint below. So the normal approximation, this we can do. It's like a typical finite block information theory paper. So it's 100 pages long and a lot of math, but you can do it. But yeah, everything gets more cumbersome.